Have you ever looked up at the stars and just felt, I don't know, the sense that there's some kind of secret language, some hidden rules running the whole show?
Oh, absolutely. And, that feeling, it's not wrong. There really is a kind of hidden operating system to the universe.
And that's what we're diving into today, right? This deep level of reality, the quantum realm.
Exactly. And the rules down there at that tiny scale, oh, they're bizarre. Really counterintuitive compared to, picking up your coffee cup.
So different from our everyday world. But you're
Ah.
saying these tiny weird rules actually shape everything, the whole cosmos.
That's the astonishing part. The very small dictates the very large. How particles behave fundamentally sets the character of the entire universe. From stars to galaxies, they're deeply linked.
Wow, okay. But it's notoriously tricky to get your head around, isn't it? I always think of that Richard Feynman quote.
Whoever claims to have understood quantum physics has not understood it.
Yeah.
It's a classic. He was right.
Why is it so hard? Is it just that we can't picture it?
I think that's a big part of it. Our brains evolved for this world, the one we see and touch. The quantum realm operates on logic that just doesn't match our everyday intuition. It goes beyond easy visualization.
Okay. So, fair warning, things might get a bit strange.
Hey, just a bit. But the goal here isn't to confuse everyone.
Right. On this deep dive, we want to shed some light on the key ideas, why they matter, without, drowning in equations.
It's about the wonder of it, the implications, seeing how the incredibly small has this huge influence.
So where do we start? The very beginning.
Let's do it. The birth of everything, the Big Bang, that first fraction of a second, unbelievably hot, unbelievably dense.
And in that instant, boom, all the basic building blocks, the fundamental particles just appear.
Poof, everything that makes up you, me, the stars.
Mm-hmm.
All the raw ingredients created right then. It's quite something to think about.
All the quarks, electrons, all that stuff.
That's the stuff. And they didn't just hang around on their own. Things happen fast.
They started pairing up.
Very quickly. Within the first 3 minutes, quarks glom together to make protons and neutrons.
Okay, the cores of atoms.
Exactly. And then those started fusing, making the first atomic nuclei, mostly helium.
So in just 3 minutes, we've gone from pure energy to the seeds of matter.
Pretty much. And it's crucial to get this. Everything that came later, stars, planets, life, it all built upon those initial products. That's the foundation.
Okay, foundation laid. Now let's step into the strange world of the very small. And I guess we have to talk about superposition and maybe a cat.
Ah, Schrödinger's infamous cat. It's a thought experiment, thankfully, not a real one. But it illustrates a core quantum idea beautifully.
So run us through it. The cat's in a box.
Right. With a device linked to a radioactive atom, if the atom decays, which is a random quantum event, 50-50 chance it triggers poison and, well, poor cat.
Okay.
The quantum card is this. Until you open the box and look. The atom hasn't definitively decayed or not decayed. It's in a superimposed state of both.
And because the cat's fate is linked to the atom.
The cat is also, bizarrely, in a superposition of being both alive and dead simultaneously.
Wait, so it's not just that we don't know if it's alive or dead. The theory says it's actually both.
That's the mind-bending part, yes. Before observation, reality seems to exist as a haze of possibilities.
And looking, that forces a choice.
Precisely. The act of measurement, of observation, collapses that superposition into one definite state. You open the box, you see either a live cat or a dead cat. Reality picks a side, you could say.
Wow. Our looking changes things. That's
Yeah.
fundamental. Okay, what about the other really weird one? Entanglement.
Entanglement. Yeah, Einstein called it spooky action at a distance. Imagine you order 2 meals at a drive-thru, 1 burger, 1 chicken. They put them in identical bags. You drive off, give 1 bag to your friend miles away. The moment you open your bag and see the burger, you instantly know your friend has the chicken, even before they open theirs.
Right, because there were only 2 options and they were linked from the start.
Entanglement is like that, but for particles. 2 particles can be created together, linked in a quantum way. If you measure a property of one, say, its spin, you instantly know the corresponding property of the other, no matter how far apart they are, light years even.
Instantly. Faster than light, that seems impossible.
It feels like it should break the rules, doesn't it? But experiments confirm it happens.
Yeah.
It's a deep connection that doesn't involve sending a signal in the conventional sense. It just is.
And these particles, the entangled ones, the ones in superposition, they are the most basic things, the elementary particles.
Yes, things like electrons, quarks. As far as we know, they're indivisible. The absolute bedrock of matter.
Okay, this is wild, but how did we even get here? People haven't always thought the world was made of quarks acting strangely, right? Let's rewind. From ancient ideas to the quantum revolution.
Right. It's been a long road. If you go way back, you've got the ancient Greeks. Empedocles, he thought everything was earth, water, air, and fire.
The four elements. Classic.
And Aristotle added a fifth, quintessence, for the heavens, the stars, and planets. Because they seem different, unchanging.
So for ages, that was kind of the model. Just a few basic ingredients.
For a very long time, yes. It took centuries of, well, alchemy, early chemistry, careful observation to realize the world is much richer, made of many more distinct substances.
Which eventually led to the periodic table.
Exactly, a monumental achievement. Dmitri Mendeleev, in the 1800s, arranging the known elements by their properties, even leaving gaps for ones yet to be found. That took insight.
He saw a pattern, a hidden order.
He did. And later, Henry Moseley refined it, organizing by atomic number the number of protons. That's a table we use today. It showed a deeper structure.
But what were the elements made of?
Well, back in 1803, John Dalton proposed his atomic theory. Matter is made of tiny, indivisible atoms. Each element has its own unique atom type.
And atoms combine to make molecules, like H2O, water.
Precisely. That was a huge leap, the foundation for chemistry. But it took the quantum revolution in the 20th century to explain why atoms behave the way they do, why the periodic table looks like it does. It all clicks together.
It always comes back to the quantum rules, doesn't it? Which brings us to another key idea. Waves and particles. A duality. Things aren't always one or the other.
That's a cornerstone of quantum physics. In our big world, a wave is a wave, like in the ocean, and a particle is a particle, like a baseball. Distinct things.
Makes sense.
But down at the quantum level, that distinction gets fuzzy, really fuzzy.
How do fields fit in, like magnetic fields?
Okay, think of a field as an invisible influence filling space. Electromagnetic field, for instance. If you disturb it, add energy, that disturbance can travel as a wave.
Like light. Light's an electromagnetic wave, right?
Exactly. But here's the twist. Quantum mechanics tells us that this light wave is also made of particles, tiny packets of energy called photons.
So light is both a wave and a particle.
Yes. That's wave-particle duality. And it's not just light. Electrons, things we think of as particles, can also behave like waves. It depends on how you measure them.
So they have, like, a secret identity. Sometimes they wear the wave costume, sometimes the particle costume.
That's one way to think about it. And we have categories for these quantum entities. Matter particles, the stuff things are made of, like electrons and quarks, we call them fermions.
Okay.
And the particles that carry forces, like photons carrying electromagnetism, those are bosons.
Got it. Fermions make stuff, bosons carry forces. What about mass? Where does that come from?
That involves another field, the Higgs field. It permeates all of space. Particles interact with this field, and that interaction is what gives them mass. More interaction, more mass.
And finding the Higgs particle, the Higgs boson, proved this field exists.
Yes, that was the huge discovery at CERN's Large Hadron Collider back in 2012. A major confirmation of our understanding.
The LHC, that giant ring smashing particles, is like our most powerful microscope for the ultra small.
It really is.
Yeah.
By recreating conditions like the very early universe, it lets us probe these fundamental interactions. Some call it the Big Bang machine.
Are there other big machines doing this kind of work?
Oh, yes. Facilities like the European XFEL in Germany use incredibly intense X-ray lasers. They can watch molecules in action, study materials under extreme pressures, like inside planets.
So again, linking the very small to the very large, the micro and macro cosmos.
It's all interconnected, which actually leads us nicely to thinking about the early universe again and the cosmic microwave background radiation.
The CMB, you called it the universe's baby picture.
That's a great description. Remember, the early universe was scorching hot, dense, a soup of particles. Gravity wasn't the main player yet. Particle physics ruled.
But as it expanded, it cooled down.
Exactly. And after about 380,000 years, it cooled enough for the first neutral atoms to form protons grabbing electrons to make hydrogen and helium.
And that was a big deal.
Huge. Before that, the universe was opaque, like a dense fog, because light kept scattering off charged particles. When neutral atoms formed, the universe suddenly became transparent.
And the light that was trapped could finally travel freely.
Precisely. And that light, released way back then, has been traveling ever since, stretching out as the universe expanded. Today, we detect it as a faint microwave glow coming from all directions. That's the CMB.
Wow, so we're literally seeing light from 380,000 years after the Big Bang.
We are. Its discovery in 1964 by Penzias and Wilson was massive proof for the Big Bang theory.
And does quantum physics play a role in understanding the CMB?
Absolutely. The CMB isn't perfectly smooth. It has tiny temperature variations, tiny ripples. Those ripples are the amplified echoes of quantum fluctuations from the very first moments of the universe.
So quantum randomness back then seeded the structures, the galaxies we see today.
That's the picture. Those tiny quantum jitters grew over billions of years into the cosmic web of galaxies and clusters. The quantum world shaped the largest structures imaginable.
Mind blown. Again. Okay, let's dive back into the weirdness with the puzzling behavior of light and matter. The double-slit experiment feels central here.
It is. It's maybe the experiment that captures the core mystery of quantum mechanics. Simple setup, profound results.
You fire particles, like electrons, one by one, at a barrier with two slits.
Right, and behind the barrier, there's a detector screen to see where they land.
If they were just tiny balls, you'd expect two clumps on the screen right behind the slits, like throwing tennis balls through two holes.
That's the classical expectation. But it's not what happens.
What do you see?
You see an interference pattern. Bands of many hits alternating with bands of few hits, just like you'd expect if waves were passing through both slits and interfering with each other on the other side.
Like water waves creating peaks and troughs where they overlap.
Exactly that pattern. But here's the kicker. You get this pattern even if you fire the electrons one at a time.
Phew, if there's only one electron going through, what's it interfering with?
That's the puzzle. It behaves as if the single electron somehow goes through both slits simultaneously, like a wave, and interferes with itself.
Okay, my brain hurts again. A single thing in two places at once, interfering with itself.
Welcome to quantum mechanics. It forces us to abandon simple pictures. Physicists have different ways of thinking about this, different interpretations.
Like the Copenhagen interpretation.
That's a major one, associated with Niels Bohr. It basically says, don't ask what the electron is doing before you measure it. Its properties aren't definite until measured. The measurement forces the outcome.
So the fuzziness is real until we look.
In that view, yes. Then there's the many worlds interpretation from Hugh Everett. That's even wilder.
How so?
It suggests that all possibilities encoded in the quantum state actually happen. Every time a quantum choice is made, the universe splits.
Splits. So in the double slit, there's one universe where the electron went through the left slit and another parallel universe where it went through the right.
That's the idea. Superposition isn't just a mathematical trick. It describes a branching reality. We just experience one branch. Think of a spinning coin. Many worlds says both heads and tails exist in separate realities until it lands in ours.
Whoa. Okay, these interpretations sound like science fiction almost.
They push the boundaries of what we mean by reality, but the math works, and the predictions are incredibly accurate.
And this quantum weirdness, as strange as it is, it's not just theory, it has real technological impact, right?
Hugely important. These aren't just abstract rules. They're the basis for technologies we use now and ones that are coming.
Like quantum computers, we hear a lot about those.
Exactly. A conventional computer bit is either a 0 or a 1. Simple switch.
On or off.
Right. But a quantum bit, or qubit, thanks to superposition, can be both 0 and 1 at the same time.
Okay, how does that help?
Well, if you have two qubits, they can represent 4 states simultaneously. 0, 0, 0, 1, 10, 11. 3 qubits, 8 states. The number of states grows exponentially.
So they can explore way more possibilities at once.
Vastly more. A quantum computer with just, say, 300 qubits could hold more possible states than there are atoms in the observable universe.
That's unbelievable computing power for specific kinds of problems.
Yes, things like drug discovery, designing new materials, breaking complex codes, optimizing huge systems, problems classical computers choke on. It relies directly on superposition and entanglement.
So understanding the role of observation and entanglement is key, not just for physics, but for future tech.
Absolutely. Entanglement, that spooky connection. It's not just weird, it's a resource.
Yeah.
It's fundamentally different from anything in classical physics. Measuring one particle, instantly telling you about the other, no matter the distance.
Is it fair to say these quantum effects are usually only noticeable at the tiny scale? Or can they affect bigger things?
They underlie everything, even big objects. But for large objects, those delicate quantum states get scrambled incredibly quickly by interacting with the environment. It's a process called decoherence.
Like the quantum weirdness gets washed out in the noise of the everyday world.
That's a good way to put it. It makes observing quantum effects in large systems very challenging, though not impossible.
Which brings us to the ongoing quest for understanding. Even with all this success, there are still big questions, right?
Oh, definitely. Quantum mechanics is incredibly successful, predicts things with amazing accuracy. But interpreting what it all means, there's still debate and big gaps in our knowledge.
The biggest gap being?
Probably the quest for quantum gravity. We have two amazing theories: quantum mechanics for the small, and Einstein's general relativity for gravity and the large-scale universe.
Planets, stars, black holes, the Big Bang itself.
Right. But the two theories don't play nicely together. They speak different languages, mathematically and conceptually. Trying to describe situations where both are important, like inside a black hole or the very first moment of the Big Bang, breaks our current physics.
So we need a new theory, a unified theory, that bridges the gap.
That's the holy grail for many physicists. A theory that seamlessly blends quantum rules with gravity. It's a massive challenge.
And other mysteries remain too. You mentioned asymmetries earlier.
Yeah, fundamental questions linger. Like, why does nature seem to prefer certain handedness? Why is the DNA and life on Earth right-handed, chemically speaking? Is that just chance, or is there a deeper physical reason rooted in the quantum world? These kinds of puzzles drive us forward. They remind us how much we still have to learn here at Cosmic Origins Revealed.
What a journey. From the Big Bang's first particles, through superposition and entanglement, all the way to quantum computers and the search for quantum gravity. It really is mind-bending.
It truly is. And the main takeaway, I think, is that the universe at its most basic level, it just doesn't follow our common sense. It has its own logic.
But that logic, those weird rules, they're not just abstract. They're responsible for why things are the way they are, for everything we see. And they're powering new technologies.
Exactly. It shows science is this ongoing adventure. We figure things out, but new questions always arise. There are still so many secrets waiting for us. That's the beauty of exploring Cosmic Origins Revealed.
It really highlights the profound connections across the universe, doesn't it? From the tiniest scale to the largest. Hints of deeper truths we haven't grasped yet.
It fills you with awe, really. The quest to understand it all, it's what makes science so compelling.
Well, if this deep dive into the quantum world has got your brain buzzing and sparked your curiosity, definitely check out more on our YouTube channel, Cosmic Origins Revealed.
Yeah, subscribe and join us. We're always exploring these amazing questions about the universe.
You'll find lots more mind-expanding content on Cosmic Origins Revealed. So thanks for joining us on this deep dive. We'll see you next time right here on Cosmic Origins Revealed.